It begins with a sound you can't actually hear, a deep cosmic shudder, the kind that doesn't travel through air or water or metal, but through the very fabric of space-time. A giant star, once bright enough to cast shadows across entire solar systems, has reached the end of its slow-burning life. For millions of years it stood unshakable, inflated by nuclear fire, balancing gravity with fusion in a quiet stalemate. But now, in the final second of its existence, that balance breaks. Inside its core, the temperature is more than 1 billion degrees Celsius, hotter than any furnace humans can imagine. And yet, in this instant, even that unimaginable heat isn't enough to keep the star alive. The outer layers begin to fall inward, free-falling at tens of thousands of kilometers per second, collapsing toward the core like an ocean of fire crashing into a single point. The whole star folds in on itself, faster than the mind wants to accept, faster than breath, faster than thought. Gravity stops being a gentle pull here. It becomes a tyrant. As the core compresses, atoms, those building blocks of all matter you've ever touched, seen, or loved, begin to fail under the weight. The electrons that orbit nuclei, normally so stubbornly separate, are rammed inward with such violence that they fuse into protons. The star is shredding atomic identity itself. Every atom is being unmade. The universe almost seems to hold its breath. There is a moment, an almost impossible moment, when the collapsing core has the mass of 1 or 2 suns, yet is shrinking down to a sphere no bigger than a city. The density climbs to numbers that feel like they shouldn't belong in reality. 1 trillion times the density of lead. 1 billion tons squeezed into the volume of a sugar cube matter is pushed so far beyond its familiar limits that the old rules are no longer recognizable. A strange kind of quiet descends. Not the gentle quiet of a peaceful night, but an eerie, absolute quiet. A quiet born from the crushing of space, the halting of light, the obliteration of structure inside this forming object. A teaspoon of material weighs more than the tallest mountains on Earth, not symbolically, literally. But the star doesn't collapse evenly. The outer layers, unable to slow down, slam into the new hyperdense core with catastrophic force, rebounding outward in a supernova that briefly outshines an entire galaxy. If some distant civilization were watching from the far edge of the cosmos, perhaps through telescopes not so different from ours, this burst would look like a sudden flare of cosmic anger. But what remains behind, what sits in the ashes of that explosion, is something even stranger and more powerful: a neutron-star. A city-sized sphere of nearly pure neutrons, held together by gravity so intense it bends the path of light, a place where mountains rise only millimeters high because anything taller is immediately flattened by gravity, billions of times stronger than Earth's, a place where a single square centimeter of surface could outweigh every skyscraper on the planet, a place where matter itself is pushed to, and far beyond, its breaking point. Imagine, just for a moment, hovering beside this newborn object. You wouldn't survive, of course. Nothing could survive here. But imagination is immune to gravity. You hover in a darkness broken only by the faint glow of cooling nuclear fire. Space trembles around you, stretched and distorted. Even time is reluctant, slowing down as you approach this compact monster. You might expect noise, chaos, or the roaring violence we associate with cosmic cataclysms. But neutron stars are paradoxes. Their births are explosive, but they themselves are quiet guardians of extreme physics. There is no wind, no crackle, no surface rumbling, just a silence so profound it feels like it fills the universe. It's strange how peaceful total compression can look. The star's surface is only around 20 kilometers, 12 miles across, the size of a small town, yet it packs more mass than 2 or 3 entire suns. If Earth were crushed to the same density, it would fit in the palm of your hand. And if a simple teaspoon of neutron-star matter appeared on Earth, it would punch through the crust, slice through the mantle, and burrow almost instantly to the planet's center. Not with the fiery drama of falling rock, but with the serene inevitability of gravity doing exactly what gravity does. Near this star, the rules of your everyday world don't apply. Light bends, time slows. Magnetic fields tower out of the surface like invisible mountains. Atoms, so familiar, so comforting in their structure, are meaningless here. Everything is stripped down to neutrons packed so tightly they begin to behave like a single quantum object. And yet, despite all this overwhelming strangeness, you can't help but feel a quiet sense of awe. This tiny sphere is the remnant of something once enormous. It is a fossilized core, the leftover heart of a star that lived and died long before humans learned to light a fire or carve a wheel. You are witnessing matter in its most extreme possible form, balanced just this side of collapse. If it were any heavier, it would fall further inward and become a black hole. Any lighter, and it would lose its crushing interior pressure. A neutron star is a perfect cosmic knife edge. Imagine drifting just above the star's surface, again only in imagination, because in reality you'd be torn apart by tidal forces so strong they would stretch you thinner than a strand of DNA. From this vantage point, the horizon curves sharply beneath you. Because gravity is so intense, nearly half of the star's surface is visible at once. Light that should travel straight is pulled around the curvature of space-time. In the distance, the last traces of supernova fire illuminate clouds of debris, spreading outward like a cosmic sunset. Each fragment carries with it the chemical legacy of the star, elements forged in nuclear furnaces, scattered into space where someday perhaps they may form new planets, oceans, or living beings. The neutron star itself glows faintly in X-rays, its heat still millions of degrees. Over millennia it will cool, but never truly die. It cannot collapse further unless fed new mass. It cannot expand. It exists in perfect gravitational tension, frozen in an eternal moment of almost but not quite becoming a black hole. This is where our journey begins, in the quiet center of chaos, in the aftermath of a star's last breath. And as you float here, in imagination or dream, held by nothing but curiosity and wonder, this is the perfect moment to settle your mind, to breathe slower, to let the grandeur of the cosmos soften the edges of your thoughts. Before we go deeper into what neutron stars truly are, their history, their strange physics, their mountains the size of grains of sand, I want to gently invite you to help these journeys continue. If you enjoy exploring the quiet extremes of the universe like this, consider subscribing to the channel and leave a comment with where you're listening from and what time it is there. It helps Sleepless knowledge grow, and it keeps these voyages alive. Space around you dims slightly, as if the universe itself acknowledges the pause. And now, as we move forward, the scene widens, the violence recedes, the cinematic moment softens into understanding. We begin to step away from the collapse and into the science behind it, the equations, the history, the discoveries that let us peer into this impossible object. The neutron star waits, silent and dense, a cosmic puzzle perfectly compressed, and the story continues. The first thing to understand about a neutron star is this. It is not a star in the familiar sense. It does not shine in the way the sun shines. It does not burn fuel. It has no swirling storms of plasma, no bubbling granules of convection, no fiery photosphere where light escapes. A neutron star is something far stranger, the skeletal remnant of a star that once lived a fiery, luminous life, only to meet a violent, dramatic end. To understand what it is, we have to understand what it used to be. For most of its life, a star is a balancing act. Its immense mass pushes inward with crushing gravitational pressure, while its nuclear fusion pushes outward with equal force as hydrogen fuses into helium and releases energy. This equilibrium can last millions, even billions of years, until the day it can't. When a sufficiently massive star, usually between 8 and 20 times the mass of our Sun, exhausts its nuclear fuel, its core loses the ability to push outward gravity, undefeated for the first time in the star's long life, takes over completely. The collapse that follows is astonishingly fast. The outer layers plunge inward at speeds of tens of thousands of kilometers per second, tens of thousands of miles per second, smashing into the core. In that instant, the structure of matter itself becomes a casualty. Electrons and protons are forced into each other with unimaginable pressure, merging into neutrons. Atoms collapse. Space compresses. And in less than a second, the once hot, once glowing core transforms into a sphere of nearly pure neutron matter. Some stars collapse into black holes. Others, slightly less massive, stop just short of the brink. That is where neutron stars live, on the razor's edge between existence and oblivion. The blast of the rebounding outer layers becomes a supernova, specifically a core collapse supernova, typically of type 2 or type 1b/c, depending on how much of the star's outer hydrogen or helium envelopes it lost before death. Type 2 supernovae involve stars that still have thick hydrogen layers. Type YB supernovae have lost hydrogen but retain helium. Type IC have lost both, but no matter the subtype, the core collapse itself is the same story. Matter crushed beyond the limits of atomic physics. When the light of the supernova fades, sometimes so bright it temporarily outshines entire galaxies, what remains is a compact object with almost impossible properties. This is the neutron-star. It may have a mass of 1.1 to 2.3 times the mass of the Sun, but the entire thing is compressed into a sphere only 10 to 12 kilometers, about 6 to 7 miles, in radius. Let that sink in. A star roughly the size of Greater London or Manhattan Island, but weighing more than our entire Sun. Its density is in the range of 4 times 10 to the 17th power to 8 times 10 to the 17th power kilograms per cubic meter. Numbers so large they lose meaning. For comparison, the density of water is 1,000 kilograms per cubic meter. The density of a white dwarf, already considered unbelievably dense, is around 1,000,000 times water's density. But neutron star matter? It's another 1,000,000,000 times denser than that. It's so dense that a single teaspoonful of it would weigh somewhere between 1 and 3 billion tons. A teaspoon, 1 to 3 billion tons. If a handful of neutron star matter ever appeared near Earth, it wouldn't just punch a hole through the planet, it would continue falling through, oscillating back and forth, until friction in the molten core finally damped its motion, and it settled at the absolute centre, and the planet would not survive long afterward. But this is not just an object of extreme density, it is an object of extreme physics. Every familiar rule you've ever held about matter becomes a whisper. Every intuition breaks. Imagine standing, if one could stand, on the surface of such a star. The gravity would be about 100 billion times stronger than Earth's gravity. A human body would be crushed into a flat film of matter in a fraction of a millisecond. Far faster than brain cells could even register pain. Not that time would behave normally near such a star. General relativity predicts intense time dilation near massive compact objects. A person hovering just a meter above a neutron star surface, if somehow shielded, would experience time running slightly slower than a distant observer watching from afar. Light itself feels the star's pull. The gravitational field is so intense that roughly 30 to 40% of the star's surface is visible from any vantage point. Light that would normally shoot straight upward is pulled sideways, curving around the star. To float above a neutron star is to witness physics bending around you. But all of this raises a natural question. How does this thing exist at all? Why doesn't it simply continue collapsing into a black hole? Here is where the physics becomes even more strange and elegant. When electrons and protons fuse into neutrons during the supernova collapse, the resulting neutrons form what physicists call a degenerate neutron fluid. This does not mean degenerate in the moral sense, of course. Neutron stars have extremely good manners. Rather, degenerate in physics refers to a form of matter held up by quantum mechanical pressure, the Pauli exclusion principle. which states that two neutrons cannot occupy the exact same quantum state at the same time. In simpler terms, neutrons don't like being packed too close. Even gravity billions of times stronger than Earth's cannot squeeze them beyond a certain point without triggering violent resistance from quantum rules. This quantum resistance is called neutron degeneracy pressure, and it is the main force keeping a neutron star from collapsing. But the pressure is not infinite. There is a limit, a final threshold where even neutrons cannot bear the weight. This upper limit is known as the Tolman-Oppenheimer-Volkoff limit, or simply the TOV limit. It is analogous to the Chandrasekhar limit that governs white dwarfs, but far more extreme. The TOV limit marks the maximum mass a neutron star can have before gravity overwhelms neutron degeneracy. Most estimates place it somewhere between 2.1 and 2.5 solar masses, though it depends on the equation of state of nuclear matter, something scientists are still actively debating and researching. If a neutron star exceeds this limit, say through accretion of mass from a companion star or merging with another neutron star, its collapse becomes inevitable. The neutrons are squeezed into quarks, the quarks are squeezed into a point, and the object becomes a black hole. So a neutron star is a survivor, but only barely. It exists in the narrow window between collapse prevented and collapse guaranteed. Its interior structure is layered and complex. The outer crust consists of a thin, rigid layer of iron nuclei floating in a sea of electrons. Deeper down, the electrons are forced into the nuclei, creating an increasingly neutron-rich soup. Then comes the weird stuff, the nuclear pasta layer, where matter arranges itself into bizarre shapes resembling lasagna sheets, spaghetti strands, and gnocchi-like blobs. These names sound playful, almost humorous. Physicists have a tradition of giving terrifying phenomena adorable nicknames, but nuclear pasta might be the strongest material in the universe. Deeper still is the core, likely a superfluid of neutrons behaving in quantum coherent ways. And at the very centre lies the most mysterious region, a place that might contain hyperons, or a Bose-Einstein condensate of mesons, or even a soup of free quarks arranged like the quark-gluon plasma created fleetingly in particle accelerators. Some theorists propose strange matter, where quarks of different flavours coexist in a stable exotic state. Human experiments cannot reach these densities. Every theory here is drawn from mathematics, indirect observations, and the exquisite timing of pulsars. Neutron stars that flash beams of electromagnetic radiation at us with precision better than atomic clocks. The magnetic fields of neutron stars are almost beyond comprehension. A typical neutron star might have a magnetic field 1 trillion times stronger than Earth's magnetars. Their more extreme cousins can reach fields of 10 to the power of 8 to 10 to the power of 11 Tesla. For comparison, the strongest sustained magnetic fields humans have created in laboratories are around 100 Tesla, and that's already strong enough to rip metal objects from across a room. Magnetars would distort the electron clouds in atoms, reshaping the very geometry of chemistry. But even an ordinary neutron star is astonishing. Its rotation can be breathtaking. Some newly formed neutron stars spin hundreds of times per second, and millisecond pulsars, often spun up by accreting material from companion stars, can reach rotation speeds of 600 to 700 times per second, with the record holder spinning at 716 Hz. At these speeds, the surface is moving at about 0.15 to 0.2 times the speed of light. The centrifugal force tries to fling the star apart, but gravity and nuclear pressure refuse to allow it. And yet, for all their extreme behaviour, neutron stars are stable. They can exist for billions of years, gradually cooling and spinning down, emitting faint X-rays, radio waves, or gamma-ray bursts. They can be companions to normal stars or drift alone in the darkness. Some are in closed binary systems, locked in deadly gravitational dances. Others roam interstellar space silently. One of the most poetic aspects of neutron stars is that they are both a beginning and an ending. They mark the end of a star's life, but they also reseed the universe with the ingredients for life. The supernova that births them spreads carbon, oxygen, iron, and dozens of other elements across space. And when two neutron stars eventually merge, an event observed famously in 2017 as GW170817, they create the heaviest elements we know: gold, platinum, and uranium. Much of the gold on Earth may have been created in a neutron-star merger billions of years before our sun was born. To think that your jewellery, your electronics, even your body's trace-heavy elements all owe their origin to the death throes of stars and the violent collisions of neutron stars. It gives a different perspective on what these objects mean. Every atom of calcium in your bones was forged in a star that lived and died long before Earth formed. Every atom heavier than iron likely came from cosmic catastrophes stranger and more powerful than we can truly imagine. Neutron stars are the universe's laboratories, places where gravity, quantum mechanics, and nuclear physics collide in ways we could never reproduce on Earth. They allow us to test the nature of matter under pressures beyond any experiment. They are reminders that the universe is not limited by our imagination or our comfort with familiar structures. All this contained in a sphere the size of a town. And yet, for all their complexity, the idea at the heart of a neutron star is surprisingly simple. Take a massive star. Let it burn its fuel until gravity wins. Crush its core until electrons and protons merge. Stop only when quantum pressure refuses to yield. And what you get, balanced on the thin line between collapse and stability, is a neutron star. A mountain on Earth rises kilometers high. A mountain on a neutron star rises just a few millimeters because gravity flattens everything instantly. If you could somehow lay your hand on its surface, the crust would feel smooth, cold, and unyielding. A shell of iron nuclei compressed into a lattice billions of times stronger than steel. Beneath that crust is chaos, extreme physics, and the most exotic states of matter in existence. This is the neutron star, a tiny, dense, unfathomably heavy remnant of something once immense and bright. A star's legacy, compressed into a single breath of cosmic time. And its existence raises deeper questions. What happens when matter is pushed to its absolute limits? What lies beneath the crust? How do these objects spin, pulse, and crack? What stories are locked inside their magnetic fields? We stand now at the threshold of those answers, ready to descend further into their mysteries. And the journey continues. It's easy to imagine neutron stars as a modern revelation, the kind of discovery you'd expect to come from futuristic telescopes, orbiting observatories, or gravitational wave detectors humming in underground tunnels. But the story of neutron stars begins much earlier, in a far quieter setting. A laboratory in Cambridge in the early 1930s, where a young physicist named James Chadwick was puzzling over a mystery. In 1932, the world still believed that atoms consisted of a dense, positively charged nucleus of protons surrounded by a cloud of negatively charged electrons, simple, clean, balanced. But the math didn't work. Many atomic nuclei were heavier than their number of protons could explain. Something unseen was adding weight. Chadwick suspected there was a missing particle, one with no electric charge and thus invisible to the usual detection methods. Earlier physicists had speculated about such a thing, but no one had confirmed it. Chadwick decided to try. He bombarded beryllium with alpha particles and observed a peculiar kind of radiation being emitted. This radiation could knock protons out of paraffin wax, which only made sense if the radiation carried mass but no charge. Charged particles would have been deflected or absorbed. This radiation passed straight through. He tested and retested, measuring the energies, comparing angles, eliminating every alternative explanation. And then, in 1932, he published the result: the neutron exists. It was a quiet announcement, almost modest. A few pages in a scientific journal. No fireworks, no cosmic imagery. But Chadwick had opened the door to an entirely new realm of physics, a realm where matter could be stripped of its electrons, its protons, even its atomic structure, leaving behind pure neutrons in a form that did not exist naturally on Earth. Chadwick did not know it yet, but far above his laboratory, in the hearts of massive stars dying in distant galaxies, entire spheres of these neutrons were forming as part of nature's violent recycling process. His discovery was the first domino. 2 years later, in 1934, 2 other physicists picked up the idea and pushed it into the cosmos. Walter Bardy and Fritz Zwicky, working at the California Institute of Technology, were studying supernovae, those sudden, brilliant explosions that temporarily outshine entire galaxies. Observations suggested that supernovae released astonishing amounts of energy. The question was, what remained afterward? Bard and Zwicky proposed an answer that must have sounded almost outrageous at the time. Supernovae could leave behind a star made primarily of neutrons, a neutron star, not a white dwarf, not a black hole. Something else, something in between, something dense beyond human imagination. In their paper, they described neutron stars as incredibly compact objects formed when electrons and protons are forced together during a supernova. The idea was radical, almost speculative, but physically elegant. Still, in the 1930s, no telescope on Earth could detect such an object. Their theoretical neutron stars remained hidden, tucked away in the dark, waiting for technology to catch up. And so the idea slept. Not forgotten, but resting. Decades passed. The world changed. New wars began and ended. Radio astronomy was born after World War II as radar technology matured. Telescopes grew larger, more precise. Humanity entered the space age. And then, in 1967, on a cold winter evening in Cambridge, the next piece of the puzzle fell into place. Jocelyn Bell Burnell was a graduate student at the time, working with Anthony Hewish to build and operate a new radio telescope, a sprawling forest of wooden poles and wires stretched across the countryside, designed to study interplanetary scintillation. It was not elegant, it was not beautiful, but it worked. Day after day, Bell Burnell pored over rolls of chart paper, kilometres of it, searching for tiny fluctuations in radio signals. It was tedious, relentless work, the kind few people have the patience to do. And then, one day, she noticed something odd, a bit of scruff on the paper that did not look like any known radio noise. When she zoomed the chart recorder to higher resolution, the oddness sharpened. The scruff became a series of pulses, evenly spaced, repeating every 1.337 seconds with extraordinary precision, too precise to be noise, too regular to be anything terrestrial. She checked for interference. She checked for satellites. She checked for radar. She checked for objects on Earth that might create periodic signals. Nothing matched. This mysterious signal seemed to come from a single point in the sky. Her colleagues half-jokingly named the source LGM1, Little Green Men 1, because the regularity was so striking that, for a moment, the idea of an alien beacon didn't seem completely absurd. But as more sources were discovered, each pulsing with different periods, that idea evaporated. Bell Burnell had discovered the first pulsar, a rapidly spinning neutron star beaming radio waves like a cosmic lighthouse. The theoretical neutron star had become a physical, measurable object. Bard and Zwicky's idea had found its proof. Bell Burnell's discovery was one of the most important in the entire history of astrophysics. Pulsars were not just exotic remnants, they were clocks more precise than anything humanity had ever built. They allowed physicists to test relativity, measure the structure of the galaxy, probe states of matter invisible to Earth-bound laboratories, and they confirmed that neutron stars were real. The discovery should have earned her a Nobel Prize, though history famously mishandled that moment. The 1974 Nobel Prize in Physics was awarded to Anthony Hewish and Martin Ryle. Hewish for the discovery, Ryle for unrelated work. Bell Burnell, who actually identified the pulsar, was excluded. She has since handled this injustice with remarkable grace. but the scientific community knows the truth. The pulsars we study today were found because she recognized something strange in the noise. After 1967, the field exploded with discoveries. In 1971, astronomers identified the first X-ray pulsar, HER X1. Unlike the radio pulsars found by Bell Burnell, HER X1 emitted intense X-ray radiation. It was part of a binary system, a neutron star siphoning material from its companion. As this matter spiraled inward, heating to millions of degrees, it formed hotspots on the neutron star's surface that flashed with each rotation. HER X1 proved that pulsars were not only isolated stars but also violent participants in stellar relationships, feeding off their partners in cosmic cannibalism. Radio pulsars, X-ray pulsars, binary neutron stars. Slowly, a new cosmic zoo was taking shape. By the 1980s and 1990s, space-based observatories were giving humanity sharper eyes. The Einstein Observatory, the Rosat mission, the ASCA telescope, each revealed new behaviours, new signals, new glimpses into the violent lives of neutron stars. But the real revolution began when Chandra, NASA's flagship X-ray observatory, launched in 1999. Its mirrors, polished smoother than any optical surface humans had ever created, gave astronomers the ability to see the aftermath of supernova in exquisite detail. With Chandra, scientists saw neutron stars cooling. They saw jets of particles shooting from their magnetic poles. They saw hotspots dancing across their surfaces. They saw pulsars creating shockwaves in nearby gas. They saw magnetars releasing brief flashes so powerful they momentarily altered Earth's ionosphere. Other telescopes joined the effort. The XMM Newton Observatory, run by the European Space Agency, the Suzaku satellite, and numerous ground-based detectors that studied radio pulsars with unprecedented timing accuracy. But even all this was only the prelude to the modern era, an era when humanity gained the ability not only to see neutron stars, but to hear them, in a sense, through the vibrations they sent across space-time. In 2015, the LIGO detectors in the United States made the first direct detection of gravitational waves, confirming a key prediction of Einstein's general theory of relativity. But the real breakthrough for neutron stars came 2 years later, in August of 2017, when both LIGO and its European counterpart, Virgo, detected a new kind of signal, not the deep, warbling echo of merging black holes, but a higher-pitched, faster chirp. This was GW170817, the first observed merger of two neutron stars. The event lasted over 100 seconds, an eternity in gravitational wave physics, and for the first time in history, telescopes across the world watched the same event unfold in light gamma-ray bursts were detected 2 seconds after the merger. Visible light and ultraviolet radiation followed, then infrared, then X-rays, then radio waves. It was a cosmic symphony, a multi-messenger masterpiece, and it confirmed something stunning. Neutron star mergers create heavy elements like gold and platinum. Every ring on a finger, every platinum wire in a laboratory device, every grain of rare heavy metal in the crust of Earth, all were sculpted in neutron star collisions billions of years ago. In the same period, humanity also built instruments to study neutron stars more intimately. The NICER telescope, Neutron Star Interior Composition Explorer, mounted on the International Space Station, began mapping the surfaces of neutron stars by measuring their X-ray pulse profiles. It traced hotspots rotating around the surface. It measured the gravitational bending of light. It allowed scientists to infer mass and radius with unprecedented precision. Through NICER, we learned that neutron stars are not perfect spheres. Their rapid rotation distorts them, turning them into oblate, slightly bulging shapes. We learned that their surfaces can change over time. We learned that their magnetic fields create hotspots that shift location, and we learned, indirectly, that their cores may contain matter in forms we have never encountered on Earth. Today, neutron stars are no longer theoretical curiosities or mathematical footnotes. They are central players in modern astrophysics. Dozens of radio telescopes track pulsars with microsecond precision. X-ray satellites watch their eruptions and cooling patterns. Gamma-ray observatories detect magnetar flares, and gravitational wave detectors listen for the rumble of distant mergers. And yet the story is still unfinished. We still don't know exactly what lies in their cores. We don't know the true height of their mountains, the millimetre-scale bumps held up by crusts stronger than any terrestrial material. We don't know the full details of how their magnetic fields evolve. We don't know how many exist in the galaxy, or why some pulsars suddenly glitch, jumping in rotation speed in a fraction of a second. Every new telescope sharpens the picture. Every new observation shifts the puzzle. Every neutron star is its own experiment, a laboratory that nature has built for us, far beyond the pressures and densities we can create on Earth. From Chadwick's modest neutron, to Bard and Zwicky's bold prediction, to Bell Burnell's rotating cosmic beacons, to her X1's X-ray flashes, to the modern era of NICA, Chandra, XMM Newton, and gravitational wave detections. The history of neutron stars is a story of patient discovery, a story of humans noticing something strange, asking questions, building instruments, looking deeper, and finding that the universe is always stranger than expected. And the deeper we look, the more these little stars, these collapsed, humming remnants of dead giants, reveal themselves to be among the most fascinating objects ever found. They are the universe's densest memories, cosmic fossils, and also engines of creation, and our understanding of them is only just beginning. If you could peel back the crust of a neutron star, gently, like lifting the shell of an egg, what you would see inside would not resemble anything found on Earth. It would not resemble anything found in the solar system, or in laboratories, or even in the violent interiors of ordinary stars. You would be staring into a realm of matter so strange, so compressed, and so drastically redefined that even the most advanced physical theories tremble a little at the edges. Most cosmic objects reveal themselves when you study them closely. Stars show convection patterns, granules, magnetic loops. Planets reveal geology and chemistry. But neutron stars resist the gaze. They force us to guess, infer, simulate, and argue. To this day, the interior of a neutron star is one of the great ongoing mysteries of astrophysics. Balance between what we can observe, what we can calculate, and what we can only imagine with the best equations we have. The crust is the beginning of that mystery. The outermost layer of a neutron star is surprisingly thin, perhaps just a kilometre thick, but unimaginably dense. It is made mostly of iron nuclei, arranged in an incredibly strong crystal lattice, bathed in an ocean of free electrons. Think of it as a metallic landscape, but one where metal is a word stretched far beyond its usual meaning. The pressure here is so intense that electrons roam freely, forming a sea rather than orbiting atoms. The crust is smooth, unbroken, and rigid, able to withstand gravitational forces billions of times stronger than anything on Earth. If you could stand on it, and of course you couldn't, it would feel utterly unyielding, the hardest surface in the universe. The crust has to be extraordinarily strong, because it holds the star's rotation-induced deformations, including those tiny mountains only millimeters tall. Theoretical models suggest the crust may be 10 billion times stronger than steel. But the deeper you go, the stranger things become. Beneath the outer crust lies the inner crust, a region where the familiar rules of matter begin to crack. Pressures here are so immense that iron nuclei grow larger, absorb more neutrons, and begin to deform into shapes dictated not by chemistry, but by nuclear physics under extreme stress. This is the realm of nuclear pasta. The name sounds whimsical, playful even, like something that should belong on a dinner plate instead of inside an object capable of bending space-time. But physicists named it that because the shapes predicted by quantum simulations resemble familiar pasta forms. Long tubes like spaghetti flat sheets like lasagna, gnarly clusters like gnocchi, Swiss cheese structures full of holes, interconnected networks like nervous tissue. These shapes aren't aesthetic choices. They are the lowest energy configurations of nuclear matter under a tug-of-war between two competing forces. The strong nuclear force, which wants to bind protons and neutrons tightly together. Coulomb repulsion, the tendency of positively charged protons to push apart. Meanwhile, gravity presses down with unimaginable intensity. The only way to balance these competing pressures is with these bizarre geometries, shapes that maximize packing efficiency while minimizing energy. Nuclear pasta may be one of the strongest materials in existence, perhaps the strongest. If you could touch it, very hypothetically, and preferably with a robotic arm made of theoretical matter that doesn't exist, it would neither feel like solid nor liquid. It would feel like something entirely new. A super-dense, semi-flexible matrix of nuclear configurations that do not exist anywhere else in the cosmos. Go deeper still, and everything familiar dissolves. Below the nuclear pasta layers lies the outer core, a region of superfluid neutrons. Superfluid is another word that stretches imagination. A superfluid has zero viscosity. It flows without friction, without resistance, without turbulence. It can climb the walls of a container. It can swirl endlessly without slowing. In neutron stars, the neutrons here behave collectively, like a single quantum object extending across kilometers. If you could swirl this superfluid, it would swirl forever. But the outer core is not just neutrons. There are also some protons and electrons mixed in, subatomic minorities struggling to exist amid the overwhelming neutron population. The proportions vary with depth and equation of state, but one thing is certain: this region is dominated by quantum mechanics on the most massive scale imaginable. Below the outer core lies one of the great scientific battlegrounds of our age, the inner core. We don't know exactly what's here. No instrument on Earth can compress matter to these densities. No experiment can replicate the combination of gravity, pressure, and quantum confinement found inside a neutron star. All we have are mathematical models, theoretical extrapolations, and indirect observations gleaned from pulsars, glitch events, cooling curves, gravitational wave signatures, and X-ray pulse profiles measured by missions like NICA. Theories abound, and each is stranger than the last. One possibility involves hyperons, particles containing strange quarks. Hyperons are unstable on Earth, decaying in tiny fractions of a second, but inside a neutron star they could exist long enough to matter. They might form a dense soup in the deepest regions, altering the star's mass-radius relationship and changing how the star responds to pressure. Another idea proposes pion condensates. Pions are particles that mediate the strong nuclear force. Under extreme densities, they may form a collective state, something like the nuclear version of a Bose-Einstein condensate, a macroscopic quantum phenomenon where all particles occupy the same state. Pion condensates would dramatically soften the equation of state, allowing the core to compress more easily. Even more exotic than pions are kaon condensates. Kaons contain strange quarks and, at the crushing densities of the inner core, could form a condensate similar to pions but even stranger. If kaons condense, they could drastically reduce the pressure support inside the star, possibly influencing the TOV limit, the maximum mass a neutron star can have before collapsing into a black hole. And then there is the most dramatic possibility of all quark-gluon plasma. This is matter stripped to its fundamental constituents. No protons, no neutrons, no atomic structure at all. Instead, the quarks that make up neutrons and protons Up quarks, down quarks, maybe even strange quarks, roam freely in a soup of gluons, the carriers of the strong force. Such a plasma exists for brief instants in particle colliders like the Large Hadron Collider, but only at extremely high temperatures and extremely low densities compared to neutron stars. If the inner core is made of quark, gluon plasma, then neutron stars aren't neutron stars at all. They're quark stars. Or, if strange quarks dominate, perhaps strange stars. Some theorists even suggest that strange matter, once formed, could be more stable than ordinary matter, potentially leading to entire populations of strange quark nuggets roaming the cosmos. Yet another layer of exoticity awaits. Color flavor, locked matter. This is not poetic language, it's technical. In this state, quarks pair up in a way analogous to electrons pairing in superconductors, but quarks have more degrees of freedom. Color charge, red, green, blue, and flavor, up, down, strange. In the color flavor locked phase, quarks form Cooper pairs that align both color and flavor in specific ways. This would create a superfluid, superconducting core unlike anything ever imagined. This idea is beautiful in its symmetry, almost artistic in its mathematical structure. If nature really implements it at the center of neutron stars, then the universe contains regions where quarks dance in perfectly coordinated quantum patterns. An elegant, crystalline chaos, impossible to visualize and yet profoundly compelling. All of these theories, hyperons, pion condensates, kaon condensates, quark-gluon plasma, color flavor locked matter, are attempts to answer the same question. How does matter behave when the strong nuclear force and gravity reach their absolute limits? This is where the uncertainty comes from, uncertainty rooted not in ignorance, but in the fundamental complexity of quantum chromodynamics, QCD, the theory describing quarks and gluons. QCD is brutally difficult to solve at the densities inside neutron stars. The equations become tangled, non-linear, almost rebellious. They refuse analytic solutions. They defy our computational power. They whisper answers rather than proclaim them. We study neutron star interiors indirectly, from the way pulsars slow down, from how they glitch, jumping suddenly in rotation speed, from gravitational waves that reveal tidal deformability, from X-ray pulse profiles that show how light bends around their surfaces, from cooling rates over millions of years. But even with NASA on the International Space Station, extracting the inner core structure from surface observations is like deducing the flavor of a cake by measuring the pattern of crumbs on the plate after it's eaten. Still, every observation narrows the possibilities. In recent years, gravitational wave detections from neutron star mergers have offered new clues. When two neutron stars spiral into each other, their tidal distortions reveal how stiff or soft their interiors are. The chirp signal, the rising frequency of gravitational waves, encodes information about compressibility. The kilonova aftermath shows how much matter was ejected and at what speed. With each event, we learn a little more, and the answers we glimpse suggest that the core is neither too soft nor too stiff, a hint that exotic matter may indeed exist, but in carefully controlled proportions. Perhaps part hyperonic soup, part quark-gluon mix, perhaps a layer of color flavor locked matter deeper down, with a nuclear pasta boundary above it. Perhaps something no one has imagined yet. Whatever lies within, one thing is certain. The inside of a neutron star is the most extreme laboratory in the universe, not one we can walk into, not one we can build, but one we can observe across light years through the precision of pulsars, the outbursts of magnetars, the cooling of X-ray surfaces, and the faint whispers of gravitational waves. It is a place where physics reaches its breaking point, and then invents new rules to survive. As we move deeper into their mysteries, neutron stars continue to challenge and inspire us. They hold secrets about matter itself, about the early universe, about the strong nuclear force, and about the ultimate limits of physical laws. If you were to approach a neutron star and look closely, truly closely, At its surface, you might expect to see jagged ridges or volcanic scars or something resembling the landscapes we know from planets and moons. After all, this is the surface of a star that has been crushed to densities beyond imagination. Shouldn't it look dramatic? Shouldn't it resemble chaos frozen into form? But it doesn't. A neutron star's surface is almost perfectly smooth. To understand why, you need to picture the star's crust, a layer only a kilometre thick, but so strong and so compressed that its properties almost defy language. It is often described as the strongest known material in the universe, a statement that sounds like hyperbole until you look at the numbers. Laboratory-grade steel, the stuff used in skyscrapers, ships, and spacecraft, can withstand stresses of maybe a few gigapascals. The crust of a neutron star can tolerate stresses approximately 10 billion times greater. That's not a poetic exaggeration. It is literally 10 billion times stronger than steel. This crust is composed primarily of iron nuclei arranged in an ultra-rigid lattice, suspended in a sea of degenerate electrons. As you move deeper, the nuclei become increasingly neutron-rich, larger and stranger in structure. They deform, stretch, and eventually meld into the nuclear pasta geometries that lie below. But in the outermost kilometers, the crust behaves like a colossal cosmic steel plate, smooth, crystalline, and unbelievably stiff. Yet even this supermaterial can't resist the titan it sits upon. The surface gravity of a neutron star is roughly 100 billion g, meaning 100 billion times the gravitational acceleration you feel standing on Earth. Such gravity flattens everything. Not metaphorically, literally. On Earth, mountains can rise kilometers high because the planet's gravity is relatively weak and because the rock beneath them can support their weight. In contrast, on a neutron star, gravity is so overpowering that a mountain taller than a few millimeters would instantly collapse under its own mass, melting back into the surface like a sandcastle dropping onto a steel plate. This is why neutron stars appear so smooth. Even the tallest mountains are mere ripples. A millimetre or two, perhaps the height of a grain of rice, if the crust is strong enough to support them. These structures are sometimes called neutron-star mountains, though the term barely conveys their microscopic scale. They are tiny, yes, but their consequences are enormous. To understand why such tiny bumps matter, we need to think about the physics of rotation. A perfectly smooth sphere spinning in space emits no gravitational waves. It is symmetrical. Everything balances. But a sphere with even a tiny imperfection, a bump, a dimple, a millimetre-high ridge, becomes a rotating mass that is slightly out of balance. This imbalance causes the star to emit ripples in space-time. That is, a neutron star mountain, only a millimetre tall, can generate gravitational waves. This idea was explored in depth in a landmark study by physicists Ushomirsky, Cutler, and Bildston, 2000. Their question was simple but profound. How big can these mountains be? Their calculations used the physics of the crust's shear modulus, its resistance to deformation, and the star's gravitational field to determine the maximum ellipticity the crust could support. In simpler language, they asked, what is the largest deviation from perfect spherical symmetry a neutron star can sustain without collapsing under gravity? The answer, according to their analysis, was that the crust could support mountains of a few centimetres at most under extreme conditions, but more realistically, a few millimetres tall. This tiny bump, no larger than the height of a fingernail, could generate detectable gravitational wave signals if the star is spinning rapidly. A neutron star spinning hundreds of times per second becomes a sort of gravitational wave whistle, radiating space-time ripples at frequencies proportional to its rotation. If it has even a slight asymmetry, the imbalance produces periodic distortions as it spins. The stronger the asymmetry, the stronger the waves. Most neutron stars are likely very smooth, their surfaces nearly perfect, but some, especially young, hot ones with active magnetic fields, may have small distortions frozen into their crusts. Others may develop them over time as their magnetic fields twist and tug the crust, or as accreted matter piles on in uneven ways from companion stars. Imagine watching such a star rotating in the dark. You wouldn't see the millimeter-scale mountain, you wouldn't hear anything in the ordinary sense. But space-time itself would tremble in rhythm, carrying whispers across light years. Gravitational waves stretch and compress space by minuscule amounts, fractions of the width of a proton, yet detectors like LIGO and Virgo can sense these tremors from distant stellar collisions. Continuous gravitational waves from neutron stars would be far weaker than merger signals, but still theoretically detectable if the deviations are large enough or if the star is close enough to Earth. So far, no continuous gravitational waves have been confirmed, but the search continues because finding such a signal would give us direct insight into the crust's strength, its breaking point, and the internal composition of these stars. It would allow us to measure their ellipticity, calculate their physical rigidity, and even infer the behavior of matter deep inside the core, something we cannot observe directly by any other method. The crust is more than just a hard surface. It is a gateway into the physics beneath. Small fractures in the crust, called starquakes, can occur when the magnetic field rearranges itself, or when the star's rotation slows and its shape adjusts. These quakes release enormous amounts of energy, sometimes detected as sudden bursts of X-rays or shifts in the pulsar's rotation rate. They are the echoes of stresses deep within the neutron star, stresses far beyond anything experienced or imagined on Earth. A starquake is not like an earthquake. When Earth's crust shifts, plates grind and rupture slowly, but a neutron star's crust, when stressed to the limit, snaps violently, releasing as much energy as a global catastrophe. The crust returns to equilibrium, smoothing out its shape, correcting any accumulated asymmetry. In a sense, starquakes make neutron stars even smoother over time. Yet in some cases, the quakes may build tiny mountains, fractures or accumulations of matter that don't immediately collapse. These imperfections become potential sources of gravitational waves. The study by Ushamirsky, Cutler and Bilston helped formalize this concept, showing mathematically that crustal deformations could sustain detectable ellipticities in rapidly spinning neutron stars. Their work remains one of the cornerstones of neutron star physics, guiding gravitational wave observational strategies even decades later. What makes this so compelling is the scale of the contrast. A millimeter-tall mountain on a neutron star has more gravitational significance than Everest has on Earth. Everest is a gentle bump on a sphere over 12,700 kilometers, about 7,900 miles in diameter. A neutron star mountain is a bump on a sphere only 20 kilometers, about 12 miles across, rotating at hundreds of times per second, generating gravitational ripples from distortions nearly invisible to the human eye. This is one of the subtleties of cosmic physics. The biggest consequences often come from the smallest imperfections. A neutron star's crust is not merely a shell, it is a pressure cooker of nuclear forces, where iron nuclei lock together like a planetary armor plate, resisting forces that would crush anything else in the cosmos. It carries the stresses of rotation, the twists of the magnetic field, and the distortions of accretion processes. It supports microscopic mountains capable of altering the very fabric of space-time. And beneath it lies a complex, layered interior, full of quantum fluids and exotic states of matter, pushing upward while gravity pushes down. The balance between these pressures determines the star's final shape, its seismic activity, and its ability to wobble or radiate gravitational waves. Standing at the surface, imagining drifting above it, one must appreciate that the crust is the thin boundary between the observable universe and a region of matter at densities that crush imagination. It is the visible skin of a mystery that continues inward like nested layers of complexity. And yet, it is this thin crust that dictates so much of the star's behavior, how it rotates, how it emits radiation, how it interacts with companions, how it quakes, how it ages. It is the crust that holds the star's history. It is the crust that reveals the star's imperfections. It is the crust that tells us how strong matter can become. And even though its mountains are tiny, delicate millimeter-scale ridges, they are among the most important features in neutron-star astrophysics. They are reminders that even the smallest deviations can have cosmic consequences. More mysteries lie beneath this crust, and more questions swirl around the physics of the layers below. But for now, it is enough to pause here, at the boundary between the familiar and the impossible, and recognize just how extraordinary a neutron star's surface truly is. When we look deeper, new extremes await. To understand a neutron star, you have to set aside your everyday intuition about gravity. Gravity on Earth is gentle, an invisible pull that keeps your feet on the ground, that shapes rivers, that sculpts landscapes over eons. At its strongest on Earth, gravity feels firm. On a neutron star, gravity is something else entirely. It is a force so overwhelming that even the concept of standing ceases to make sense. The surface gravity of a neutron star is roughly 100 billion G, not 100, not 1,000, 100 billion times the gravitational acceleration on Earth. If you could somehow hover just above the surface, protected by some impossible machine that prevented you from being torn apart, you would see the curvature of space-time so extreme that space seems almost to fall away beneath you. The idea of down becomes absolute, a direction commanded by gravity with total authority. In such a place, even light struggles to move freely. According to general relativity, mass curves space-time, and the more compact the mass, the more severe the curvature. A neutron star is so compact that if you hover above it, you don't simply see the hemisphere facing you, you see 30 to 40% of the entire star at once. Light that should travel sideways instead arcs upward, pulled around the star's curvature. Photons that try to escape must climb a steep gravitational well, losing energy along the way. This warping of light makes a neutron star appear swollen, its edges lifted into visibility like a horizon bent inward. The effect is disorienting. You look at the surface and see more than you should, as if the star is turning its hidden side toward you. This bending of light is not just a visual curiosity, it's a window into the star's gravity. Observatories like NICA use this bending to reconstruct the shape of hotspots on a neutron star's surface. As these hotspots rotate into and out of view, their brightness changes in ways that reveal the star's mass, radius, and even the stiffness of the matter inside. Gravity does not only bend light, it changes the light itself. Photons escaping from the surface of a neutron star undergo gravitational redshift. That is, their wavelengths stretch as they climb out of the star's gravitational field. A photon emitted as an X-ray at the surface will be detected at a slightly lower energy farther away. It is as if gravity itself steals a little of the photon's vigor on the way out. This redshift isn't subtle. For a typical neutron star, the gravitational redshift factor might be around 0.3. That means light loses about 30% of its energy as it escapes. On Earth, gravitational redshift is measurable only with extreme precision and careful experiments, like those using atomic clocks at different altitudes. On neutron stars, it is a daily fact of existence. The escape velocity from a neutron star's surface is another expression of its ferocious gravity. On Earth, escape velocity is 11 kilometers per second, about 7 miles per second. On a neutron star, escape velocity is roughly 0.4 times the speed of light, nearly 120,000 kilometers per second, about 74,500 miles per second. Nothing slower than that can reach freedom. Anything thrown upward, rocks, dust, atoms, falls back immediately. Even light barely makes it. A spacecraft trying to leave a neutron star would need engines capable of pushing it to relativistic speeds, a feat far beyond any technology humans have ever imagined realistically. In practice, nothing escapes except light, neutrinos, and sometimes a little plasma pulled away by intense magnetic fields. The gravity is so intense that it accelerates particles to incredible energies. Charged particles near the surface spiral along magnetic field lines at nearly the speed of light, producing powerful radiation. These processes contribute to pulsar emission and magnetar flares, phenomena that would be impossible in weaker gravitational environments. But perhaps the most haunting effect of neutron-star gravity is its influence on time itself. Einstein's equations show that time moves more slowly in stronger gravitational fields. On Earth, the effect is tiny. Clocks placed on a mountaintop tick slightly faster than those at sea level, but the difference is so small that only highly calibrated atomic clocks can measure it. On a neutron star, the effect becomes dramatic. If you hovered a few meters above the surface, protected by hypothetical technology, and looked upward toward space, you would see the universe running faster. Stars would drift through their positions slightly quicker. Pulsars in the distance would appear to spin a little faster than usual. Conversely, an observer far away would see your time moving slowly. Seconds near the neutron star might look compressed, dampened, stretched out. The deeper you are in the star's gravity well, the more time slows relative to anyone observing from afar. This differential aging is not science fiction, it's a measurable consequence of general relativity. If a twin were able to hover above a neutron star surface while the other remained far away, the hovering twin would age more slowly. The effect would not be subtle. A person spending years near a neutron star could return to find decades or even centuries had passed for those who stayed away. This isn't because the neutron star steals time, but because time itself stretches and compresses in the curved geometry of space-time. If you could step outside the universe and look at space-time the way you might look at a topographical map, you would see the neutron star sitting in a deep, steep well, a pit carved into the fabric of reality. Clocks nearer the bottom of that pit run slower. Clocks near the top run faster. Hovering near the surface, even with theoretical shielding, would feel like existing in a place where reality is under tension. Space curves sharply around you. Photons climb uphill to escape. Time thickens. Every law of physics you know from Earth stretches, bends, or transforms under the weight of gravity this strong. General relativity was tested and confirmed in many ways. Mercury's orbit, the bending of starlight during eclipses, the time dilation measured in GPS satellites. But neutron stars are where relativity becomes palpable, concrete, primary. They are the ultimate test beds for Einstein's theory, pushing it to limits where the equations become deeply non-linear and space-time geometry contorts almost into collapse. Even the shape of a neutron star itself defies simple geometry. Rapid rotation makes it ablate, flattening slightly at the poles, while gravity compresses it into a nearly perfect sphere. Its surface is a compromise between centrifugal force and general relativistic curvature. The deformation is small, millimeters to centimeters, but in the context of such intense gravity, those differences matter. They influence rotation, stability, and the potential emission of gravitational waves. General relativity predicts that rotating mass should drag space-time along with it, an effect known as frame dragging. Near a rapidly spinning neutron star, this dragging becomes significant. Space itself is forced to rotate around the star, like water swirling around a whirlpool. This means that any object near the star cannot remain stationary relative to distant observers. It must move with the dragged space-time. The neutron star's gravitational well also affects how it interacts with orbiting companions. A neutron star in a binary system can produce orbital decays measurable with exquisite precision. The famous Hulse-Taylor pulsar, PSRB 1913+16, loses orbital energy exactly as predicted by general relativity. Through gravitational wave emission, measurements of this decay matched Einstein's predictions so perfectly that Hulse and Taylor received the Nobel Prize. In every direction, neutron star gravity reveals new facets of relativity. Tidal effects deform companion stars. Magnetic fields warp in unexpected ways, light curves around the object, illuminating its surface in strange patterns. And time ticks differently everywhere you look. If you imagine floating a few kilometers above the neutron-star, say 3 kilometers, about 1.8 miles, up, you would see the star's curvature filling your sky. The horizon would be sharply curved, almost bulbous. Above you, space would look normal. But below, you would sense an invisible pull so powerful it distorts your perception. Dropping even a small object, a pebble, a coin, anything, would result in an acceleration so rapid it would hit the surface at a significant fraction of the speed of light, vaporizing instantly. No atmosphere interrupts the fall, no friction slows it, gravity reigns alone. This stark simplicity makes neutron stars beautiful in a way that is difficult to describe. They are cosmic sculptures carved by gravity and defined by relativity. They are compact enough to distort light, massive enough to twist space-time, dense enough to slow time itself. They sit on the boundary between the possible and the impossible, balanced one step before collapsing into a black hole. Standing, or rather hovering, near one is like being near the edge of a vast cosmic cliff. The view is breathtaking, but the drop is absolute. Gravity rules here with such dominance that even the idea of surface becomes strange. The crust is a physical boundary, yes, but space-time itself curves smoothly through it. There is no hard distinction between inside and outside in the way we think of terrestrial objects. Everything is geometry, everything is curvature. Neutron stars remind us that gravity is not a force in the traditional sense. It is the shape of the universe. It is the bending of coordinates. It is the way time and space weave together under mass and energy. These extreme gravitational effects set the stage for everything else neutron stars do. Their rotation, their pulsations, their X-ray bursts, their magnetic eruptions, their mergers, and the gravitational waves they release. To understand a neutron star is to accept that nature plays by a very different set of rules at these scales. The deeper into their physics we go, the more startling the consequences become. If the gravity of a neutron star reveals its mass and compactness, its magnetic field reveals something even stranger. The ferocity of its birth and the extreme quantum world pinned beneath its crust. Magnetism on a neutron star is not the gentle guidance of a compass needle, nor the subtle protection offered by Earth's magnetic field. It is violence frozen into geometry. It is structure imposed on the vacuum itself. It is a force so intense that it reshapes atoms, stretches electrons, and cracks the crust of the star like brittle ceramic. To begin to grasp this, consider Earth's magnetic field, a humble, comforting 30 to 60 microtesla, just enough to steer migratory birds and give us auroras. Our field is the result of a churning, molten iron core driving a geodynamo, a vast planetary engine that hums quietly over geological time. Now consider a neutron star. Even a normal neutron star has a magnetic field between 10 to the power of 8 and 10 to the power of 11 Tesla, 10 million to 100 billion Tesla. Numbers so absurd they leave the realm of intuition. If Earth's field is a candle flame, a neutron star's is a thermonuclear explosion frozen in place. These fields are the relics of a dying star's collapse. As the progenitor star shrinks from a radius of millions of kilometers to barely 10 to 12 kilometers, 6 to 7 miles, its magnetic field is compressed, multiplied, and intensified by the conservation of magnetic flux. The magnetic lines frozen into the stellar plasma are squeezed together like threads forced into a tiny knot, raising the field strength by orders of magnitude. The result is an object where magnetism becomes one of the dominant forces shaping physics. To understand the consequences, imagine placing a hydrogen atom, just a proton and an electron, near a neutron star's surface. On Earth, that atom is round. its electron cloud forming a fuzzy sphere. Near a neutron star, the magnetic field stretches the electron into a long, thin cigar, aligned with the magnetic field lines. Chemistry itself changes, orbital shapes distort, energies split, entire elements behave differently. At field strengths above 10 to the 9th power Tesla, electrons no longer orbit nuclei in familiar shapes. Their motions become constrained to tight cyclotron loops perpendicular to the field, forming quantized Landau levels. At around 10 to the 11th power Tesla, even these quantum levels collapse into something entirely new, a place where atoms become needle-like, hundreds of times narrower than usual and much longer. Matter here is not merely compressed, it is magnetically sculpted. This affects more than atoms. The neutron star's crust, that rigid, nearly perfect lattice of iron and neutron-rich nuclei, is threaded with magnetic stresses. Imagine a metal bar twisted by forces that build invisibly, silently, over years. The bar doesn't bend, it reaches a threshold and snaps. A similar process unfolds on neutron stars. Their crust, though incredibly strong, carries immense magnetic tension that shifts slowly but relentlessly as the magnetic field evolves. When the stresses exceed what the crust can bear, it cracks. This is a starquake. The term sounds almost delicate, but the scale is apocalyptic by human standards. A starquake releases energy equivalent to the combined output of millions of nuclear bombs, all discharged in milliseconds. The cracking crust sends seismic waves rippling through the star and violently rearranges the magnetic field lines above it, sometimes accelerating particles to nearly the speed of light. The consequences can be seen from across the galaxy. Flares brighten, X-rays erupt, gamma rays burst forth in sudden, catastrophic flashes. These events are signatures of a special kind of neutron star, the magnetar. Magnetars are neutron stars, with magnetic fields reaching the absurd realm of 10 to the power of 10 to 10 to the power of 11 Tesla. They represent the most extreme magnetic environments in the universe. While typical neutron stars might live quietly as radio pulsars or X-ray pulsars, magnetars are constantly battling their own magnetism. Their fields are so strong that they twist space-time and distort vacuum into a birefringent medium, meaning empty space behaves like a crystal, splitting light into different polarization states. Near a magnetar, even the vacuum has structure. The crust of a magnetar is under almost unimaginable strain. Magnetic field lines anchored in the crust shift as the internal field evolves, but the crust cannot easily follow. It resists, it strains, it holds, until it can't anymore. Then it snaps. A magnetar starquake sends electromagnetic energy blasting outward with such ferocity that it can saturate detectors on Earth. Even when the magnetar lies tens of thousands of light years away, one magnetar, SGR 1806-20, produced a flare in 2004 so powerful that it ionized Earth's upper atmosphere and briefly altered the behavior of satellites in orbit. If such a flare occurred within 10 light years of Earth, it could sterilize the planet. And yet these quakes are simply the magnetar trying to relieve tension. Its crust cracks, rearranges, settles. Then the tension begins building again. The source of this immense magnetic field lies deep inside the star. The leading theory is that magnetars are born spinning extremely rapidly, perhaps 1 to 2 milliseconds per rotation, which allows a dynamo process to amplify magnetic fields during the first few seconds after the star's birth. The newborn neutron star, still molten and convective, generates fields that grow to staggering strength. As the star cools and solidifies, these fields become frozen in place, trapped in the crust and the interior. Once formed, the magnetic field begins a slow decay, releasing energy through heat and radiation. This decay powers magnetar activity long after the star's rotation slows. It's something ordinary pulsars do not experience to nearly the same degree. The magnetic field is not uniform. Some regions of the crust experience higher tension than others. As the star rotates and its internal structure evolves, the stress distribution shifts. When the crust gives way, the overlying magnetic field lines reconnect suddenly, much like solar flares, but magnified tremendously. This reconnection is responsible for the most intense gamma-ray flares in the universe. The magnetosphere becomes a cauldron of charged particles whipped into frenzy. Magnetic loops snap, reform, and lash out. The flare expands at relativistic speeds, heating the surface and sometimes altering the star's spin slightly. The afterglow can last hours. The star may enter a phase of erratic, unpredictable activity. It cools, it re-stabilizes, the field shifts again. Magnetars are the restless members of the neutron-star family. Most neutron stars live long, disciplined lives governed by rotation and magnetism in calm equilibrium. Magnetars, on the other hand, live in a kind of cosmic tension, always one stress cycle away from eruption. Part of what makes them so fascinating is that they reveal how much influence a magnetic field can have on matter. We often think of gravity as the dominant force in astrophysics, and in many contexts it is, but on neutron stars, magnetism becomes a sculptor of matter, a source of energy, a driver of tremors, a shaper of emissions. In environments this extreme, magnetism competes with gravity rather than yielding to it. The surface of a magnetar may be pulled outward slightly at the magnetic poles, creating subtle distortions. Magnetic pressure can rival gravitational pressure, creating regions where matter is supported against collapse by field lines alone. This interplay shapes the star's thermal evolution. Magnetars cool more slowly than ordinary neutron stars because magnetic field decay releases heat continuously, warming the crust from within. This internal heating can power X-ray emission for hundreds of thousands of years after formation. Observationally, magnetars appear as soft gamma repeaters, SGRS, or anomalous X-ray pulsars, AXPS. They pulse, but not in the same way as radio pulsars. Their emissions are dominated by magnetic activity rather than rotation. Their X-ray spectra carry the fingerprints of strong field physics. Spectral lines distorted, broadened, shifted, and sometimes split by immense magnetic influence. Even their atmospheres behave strangely. Under fields of 10 to the 11th Tesla, atoms are flattened and elongated. Ionization thresholds shift, opacities change. The surface might be partially ionized in some regions and fully condensed in others, forming a magnetic metal rather than a gas. Radiation escapes in beamed patterns that depend heavily on the angle between the magnetic field and the observer. Some magnetars possess twisted magnetospheres, tangled magnetic fields filled with currents, resembling solar prominences on steroids. These twisted fields store energy, which can be abruptly released in magnetic avalanches. Observations show that magnetars often brighten suddenly in X-rays, then slowly fade over months as the field untwists and the crust cools. The structure of these fields may extend far into space, interacting with dust, gas, or companion stars. In rare cases, magnetars in binary systems torque their companions' winds or create exotic orbiting structures. Their influence radiates far beyond their small radius. For all their violence, magnetars are fleeting phases in the life of a neutron star. After tens of thousands of years, a blink in cosmic terms, their magnetic fields decay enough for them to settle into quieter states. They fade into ordinary neutron stars or radio pulsars. Their starquakes grow infrequent, their surfaces cool, their magnetospheres relax. Yet the damage left behind, the cracked crust, the reshaped interior, the history of eruptions, remains etched into their structure. In this way, magnetars tell a story not just about magnetic extremity, but about evolution. They show how neutron stars change over time, how stresses build and release, how magnetic fields tunnel through matter and twist the vacuum into patterns of power. They reveal the limits of matter's strength, the point at which even a crust tens of billions of times stronger than steel gives way. Neutron-star magnetism is more than a scientific curiosity. It is a reminder that the universe contains forces capable of reshaping reality at the quantum level, bending vacuum, sculpting atoms, and cracking stars like shells. Yet all of this intensity, all of this energy, exists within an object only the size of a city, a tiny sphere of condensed history and ongoing transformation, where magnetism and gravity argue constantly over who gets to shape the world. The deeper we look, the stranger these arguments become, and the more the hidden life of neutron stars begins to unfold. There are moments in astrophysics where the universe feels almost too theatrical, too perfectly staged, as though cosmic phenomena were designed with a sense of dramatic timing. Pulsars are like that. They are neutron stars that spin with breathtaking speed, sweeping beams of radiation across the cosmos like lighthouse beams roaming over dark waters. Except these lighthouses spin hundreds of times per second, and the ocean beneath them is space-time. To understand pulsars, imagine a neutron star just after birth. It has collapsed from a stellar core millions of kilometers wide to a sphere barely 20 kilometers, 12 miles, across, but angular momentum, the cosmic version of once spinning, always spinning, is conserved. What once rotated slowly as a massive star now rotates ferociously as a compact remnant. This is why newborn neutron stars can spin 1,000 times or more per second, completing a rotation faster than the blink of an eye. The speed is almost absurd. Imagine a city-sized object spinning so fast that its surface moves at a significant fraction of the speed of light. The centrifugal force is immense, strong enough to flatten the star slightly at the poles. Yet gravity remains dominant, pulling every particle inward with overwhelming determination. The fastest known spinning neutron star is PSRJ, 1748-2446 AD, rotating at 716 Hz. That is, 716 rotations every second. Each rotation sweeps its magnetic poles around the universe in a tight, predictable rhythm, sending pulses of radio waves toward Earth like clockwork. Not just clockwork, better than clockwork. Pulsars are so stable that their timing can surpass the best atomic clocks humans have ever built. The rotation of some millisecond pulsars is so consistent that physicists use them as tools to detect gravitational waves passing through the galaxy, ripples in space-time that subtly stretch or compress the intervals between pulses. A typical pulsar emits a beam of electromagnetic radiation from each magnetic pole. These beams are not perfectly aligned with the star's rotation axis. As the neutron star spins, its beams sweep through space like cosmic searchlights. When one of these beams crosses Earth, we observe a pulse. Sometimes hundreds of times per second, sometimes slower, sometimes with enough precision that you could set your watch to them. This lighthouse effect is not something the neutron star chooses to do. It's a result of the extreme magnetic field and the rapidly rotating plasma around the star-charged particles spiral along magnetic field lines at nearly light speed, emitting radiation in narrow cones. These beams can include radio waves, X-rays, and even gamma rays, depending on the star's magnetic configuration and age. Young pulsars often spin faster. As they age, they slow down. This slowing is known as spin down, driven by a process called magnetic braking. A neutron star's magnetic field acts like a brake, converting rotational energy into electromagnetic radiation. Over time, the star's rotation gradually slows as it radiates away angular momentum. For a typical pulsar, the spin-down rate is small, fractions of a microsecond per year. Yet over millions of years, the effect accumulates. A pulsar born spinning at 1,000 rotations per second might slow to 100 rotations per second after a million years, and eventually to just a few rotations per second after tens of millions of years. But this slow decay is not always smooth or graceful. Sometimes a pulsar's rotation rate suddenly jumps, a phenomenon known as a glitch. These glitches are thought to occur when the superfluid interior, which rotates independently of the crust, transfers angular momentum abruptly. It's as if the star hiccups and briefly spins faster before settling again. These glitches reveal clues about the star's interior. The superfluid layers, the crust's rigidity, the coupling between layers of matter. But they also produce timing anomalies that pulsar astronomers must carefully track. Despite these occasional disruptions, the precision remains astonishing. Millisecond pulsars, especially those recycled by accreting material from a companion star, can maintain timing regularity so extreme that they rival or exceed atomic clocks. This incredible stability has led scientists to use pulsars as tools to study gravitational waves on galactic scales. By monitoring networks of millisecond pulsars, pulsar timing arrays, researchers can detect tiny changes in their arrival times caused by passing gravitational waves emitted by supermassive black hole binaries in distant galaxies. In this sense, pulsars have become not only astrophysical objects, but instruments, cosmic probes. Yet timing precision is only one part of their story. The beams of radiation from pulsars reveal intricate patterns. Some pulsars emit in radio wavelengths only, others in gamma rays. Some emit in two modes that switch unpredictably. Others exhibit delays caused by plasma in their magnetospheres. A few show drifting subpulses, repeating patterns that sweep across their pulse profiles, hinting at rotating structures within the magnetic field. Some pulsars even shut off temporarily, becoming invisible before resuming their steady pulses. These nulling pulsars and intermittent pulsars challenge our understanding of magnetospheric physics. Why do they stop? What flips the switch? What happens to the plasma environment that powers the beams? Pulsars are not dead or inert. They are dynamic. They evolve. Among the most fascinating pulsars are millisecond pulsars, which spin hundreds of times per second. These are old neutron stars that have been spun up by matter flowing onto them from a binary companion. As gas spirals inward onto the neutron star, it transfers angular momentum, accelerating the star's rotation to extreme speeds. This recycling process also reduces the magnetic field, stabilizing the pulsar's timing. The result is a compact object rotating so regularly you could measure the mass of planets around it based on small shifts in pulse arrival times. And indeed, the first exoplanets ever discovered were found in orbit around a pulsar. But beyond timing, beyond rotation, beyond their use as astrophysical tools, pulsars offer something far stranger. Connections to a type of cosmic phenomenon that has puzzled astronomers for years. Fast radio bursts, or FRBs. FRBs are intense, millisecond-long flashes of radio energy coming from distant galaxies. They appear suddenly, fade almost immediately, and release more energy in a few milliseconds than the Sun emits in days. Some fast radio bursts repeat, others remain silent after their first outburst. For years, the origin of FRBs was mysterious. Then came discoveries linking them to magnetars, neutron stars with extreme magnetic fields. In 2020, an FRB was detected from within the Milky Way, and its source was traced to a known magnetar, SGR 1935 + 154. This suggested that magnetars, especially young ones with active, unstable magnetospheres, may be responsible for at least some FRBs. The model proposes that magnetic reconnection events, the same processes that cause magnetar bursts and starquakes, can accelerate particles and produce brief, intense blasts of radio energy. Some researchers also propose that millisecond magnetars, newborn neutron stars spinning hundreds of times per second with enormous magnetic fields, might produce FRBs shortly after their birth. These millisecond magnetars could form during supernova explosions or neutron-star mergers, releasing bursts of energy as their magnetic fields snap and settle. This link between pulsars, magnetars, and FRBS has opened new questions. Why do some magnetars emit FRBS and not others? Do all millisecond magnetars emit FRBS during their youth? What conditions produce repeating FRBS? Do pulsar-like emission mechanisms play a role in the brightest bursts? Pulsars offer clues, but not yet answers. A pulsar's rotation is intimately tied to its emission. Its magnetic field dictates the shape of its beams, the dynamics of its magnetosphere, and the way its pulses propagate through space. Every pulse carries information about the star's age, magnetic field strength, spin-down rate, and interior structure. The beam angle shifts slowly as the star evolves, making some pulses visible to Earth only for thousands or millions of years. Others may spin in perfect silence from our perspective, their beams never intersecting our line of sight. From afar, the pulse sequence of a neutron star can appear hypnotic, steady, undisturbed. But up close, in the physics of the magnetosphere, in the plasma whipping around at nearly light speed, there is constant motion, turbulence, and change. The star's rotation drives its magnetic dynamo. The magnetic field structures the plasma environment. The plasma produces radiation, and the radiation escapes in beams that sweep through space. In its simplicity, spin, beam, pulse. A pulsar seems predictable. In its details, glitches, nulling, mode changes, sub-pulse drifting, magnetospheric instabilities, it is anything but. Astrophysicists are still uncovering the subtle physics inside these rotating stars. The patterns of their emission are like fingerprints, each one unique to its star. The frequency spectra, the polarization angles, the dispersion measures, all offer clues about the star's surroundings, the interstellar medium, and the structure of the galaxy itself. Pulsars are dynamic nodes in the galactic web, tiny yet immensely powerful, each broadcasting a constant rhythmic signature across the void. Some spin so fast they become cosmic hummingbirds, others spin slowly, dignified, steady, some erupt, some flicker, some change personality as though adjusting to internal stress or magnetic reconfiguration. But all are connected by the same mechanism, a rotating neutron star, compact and dense, with a magnetic axis misaligned from its rotational axis. A simple misalignment, scaled up to cosmic proportions, becomes one of the most extraordinary astrophysical phenomena ever discovered, and the story deepens further as we explore how these stars behave when they interact, collide, or tear matter from their companions. Neutron stars are already extraordinary on their own, small, dense, spinning, magnetic knots of matter that push physics to its limits. But when two neutron stars share an orbit, gravity becomes more than a force. It becomes choreography. An ancient, delicate, tightening dance that can last hundreds of millions of years until it ends in one of the most energetic events the universe can stage. These pairs are called binary neutron stars, and their story has shaped modern astrophysics, from the conformation of gravitational waves to the origin of gold in your jewellery. The first major clue that such systems existed and that they were radiating energy through a previously unseen channel arrived in 1974 with an object known as the Hulse-Taylor pulsar, officially catalogued as PSRB 1913+16. Russell Hulse and Joseph Taylor were studying pulsars when they discovered one whose timing pattern was slightly irregular. Most pulsars behave like nearly perfect clocks, but this one's signals arrived earlier and later in a pattern that looked like a heartbeat, a gravitational heartbeat. Something was tugging it back and forth. The culprit was another neutron star. This pulsar was part of a binary system, two neutron stars orbiting one another every 7.75 hours. As they circled, their intense gravity distorted space-time, generating ripples, gravitational waves, predicted by Einstein decades earlier. These waves carried energy away from the system, causing the orbit to shrink slowly. The remarkable part wasn't that this happened, theory predicted it, but that Hulse and Taylor could measure it. Each year, the pulsar's orbit decayed by a tiny amount. Its period shortened in a way that matched Einstein's equations precisely. No deviations, no errors, no alternative explanation. The system was losing energy exactly as it should if it were radiating gravitational waves. No detector existed yet to catch those waves directly, but here was their footprint. In 1993, Holson-Taylor received the Nobel Prize for this discovery, the first indirect detection of gravitational waves. It was proof that Einstein's theory worked not only on solar system scales, but in the most extreme astrophysical environments. It also revealed something else. Eventually, binary neutron stars must merge. The time it takes varies wildly. Some merge quickly, in tens of millions of years. Others take billions of years. Some may have already merged, leaving behind black holes or scattering heavy elements through space, and some, at this very moment, are spiraling inward somewhere in our galaxy, inching closer with each orbit. But for decades, astronomers waited for something more. The first direct detection of a neutron-star merger. That moment came in 2017. On August 17th, at 12:41:04 UTC, detectors belonging to LIGO in the United States and Virgo in Europe picked up a gravitational wave signal unlike any seen before. It wasn't the deep, heavy rumble of black holes merging, but a higher frequency chirp that lasted just under 2 minutes, an eternity in gravitational wave physics. This was GW170817, the first time humanity heard two neutron stars collide. The signal rose in pitch and amplitude as the stars spiraled inward, losing orbital energy and accelerating. Near the end, just before contact, they circled each other hundreds of times per second, their surfaces, dense, superfluid, riddled with nuclear pasta, stretched and deformed like cosmic taffy under enormous tidal forces. The gravitational wave signal alone was world-changing. But then something extraordinary happened. About 2 seconds after the merger, a gamma-ray satellite detected a burst of energy. It was short, just a fraction of a second, but intense. This was a short gamma-ray burst, one of the universe's brightest forms of high-energy light. For years, astronomers had suspected that these bursts were caused by neutron-star mergers. GW170817 confirmed it. And then telescopes across the world turned toward the source located in a galaxy called NGC 4993, about 140 million light-years away. They saw something new, an optical and infrared glow, fading rapidly. This was a kilonova. A kilonova is what happens when neutron-rich debris from a merger is ejected into space and begins forming new atoms, specifically heavy elements: gold, platinum, uranium, thorium, lanthanides, and actinides, all forged in the violent aftermath of merging neutron stars. The light from a kilonova carries the spectral fingerprints of these newly created atoms. Over hours and days, as the heavy element soup cools and decays, it releases radiation that astronomers can track. Before GW170817, scientists debated where most of the universe's heavy elements came from. Traditional models of supernovae couldn't account for the observed abundance of elements heavier than iron. But neutron-star mergers, with their extreme neutron-rich environments, made sense. The process responsible is called R-process nucleosynthesis. R-process stands for rapid neutron capture. In normal stellar environments, neutron capture is slow. Atoms gradually absorb neutrons, undergo beta decay, and move up the periodic table. But in a neutron-star merger, the density of free neutrons is so enormous, and the environment so violent, that atoms absorb neutrons much faster than they can decay. They leapfrog upward in atomic weight, assembling some of the universe's rarest elements in milliseconds. This is why much of the gold on Earth likely came from ancient neutron-star mergers that occurred billions of years before our solar system formed. Your wedding ring, your electronics, the gold leaf on ancient art, all bear the signature of stars that collided long before Earth existed. The kilonova of 2017 allowed scientists to watch this happening in real time. Its colour shifted from blue to red within days as different isotopes formed and decayed. Observatories measured its brightness, its spectra, its evolving temperature. Every measurement confirmed that neutron-star mergers are not only spectacular cosmic collisions, but chemical factories responsible for much of the universe's heaviest material. Meanwhile, the gravitational wave signal revealed the internal structure of neutron stars through tidal deformability, a measurement of how easily the stars distort under each other's gravity. This gave clues about the equation of state of dense nuclear matter, one of the biggest unanswered questions in physics. GW 170817 bridged entire fields: astrophysics, nuclear physics, gravitational wave science, cosmology, chemistry. It was the first multi-messenger event observed across gravitational waves and electromagnetic signals. The universe did not whisper. It sang. And beyond the kilonova and gamma-ray burst, something else happened. The merger left behind a compact remnant. What exactly formed is still debated. It might have been a hypermassive neutron star supported temporarily by rapid rotation, a supermassive neutron star that later collapsed, or a black hole formed almost immediately. Each scenario affects the amount of matter ejected, the light curves of the kilonova, and the stability of the gamma-ray jet. Current evidence leans toward a neutron star that survived briefly before collapsing into a black hole, but astronomers continue to refine their models. More mergers have been detected since 2017, but none as rich in multi-wavelength detail. GW 170817 remains a cornerstone event, a cosmic Rosetta Stone. It proved that binary neutron star systems are not theoretical curiosities, but important engines of chemical evolution throughout the universe. Binary neutron stars begin as ordinary stars, born in pairs. Through stellar evolution, each one becomes a supernova, leaving behind neutron stars that remain gravitationally bound over millions of years. Gravitational radiation causes their orbit to contract, slowly drawing them together. In the last moments, their motion becomes a spiral of escalating violence. The final seconds unfold like this. Two stars orbit faster. They stretch each other. Matter begins to strip away. Tidal tails form swirling spirals. Their cores approach collapse. Space-time trembles. They contact. They merge. A jet erupts. Heavy elements form. Light races outward. Gravity ripples across the cosmos. All of it measurable, all of it visible in one form or another. Even now, neutron star pairs remain hidden throughout the galaxy, drawing closer each day. Their futures are written in orbital decay curves, in timing variations, in subtle accelerations measured by radio telescopes. Someday, another merger will occur close enough and bright enough for us to observe as richly as GW 170817, perhaps richer. A few hundred have been identified. Millions likely exist. Some will merge within thousands of years, some within millions, some not for a billion. Yet each binary neutron star system holds within it the potential to shine as a kilonova, ignite a gamma-ray burst, forge gold, and shake space-time itself. They are reminders that the universe creates and destroys with equal intensity, and that from destruction often comes the building material of worlds. The surface of a neutron star is not a quiet place. It may look calm from afar, a smooth metallic shell suspended in the vacuum, but beneath that deceptively still veneer lies a turbulence of forces so extreme that language struggles to approach them. It is a world where the crust can crack with the violence of 10 quadrillion moonquakes, where thermonuclear fireballs erupt in milliseconds, where magnetic loops tower like invisible mountains, and where plasma made of pure antimatter forms spontaneously in fields so strong they tear the vacuum apart. Everything that happens on a neutron star's surface occurs on the knife edge between unimaginable pressure, magnetic tension, and quantum chaos. Even the smallest disturbance becomes extraordinary. Starquakes are a good place to begin because they reveal just how fragile and how powerful the crust can be. On Earth, earthquakes release energy by shifting tectonic plates. On the Moon, moonquakes occur as the surface cools and contracts. But on a neutron star, the crust is under such enormous strain, both gravitational and magnetic, that when it shifts, it releases energy on a scale far beyond anything terrestrial. A typical neutron star crust is roughly a kilometre thick, made of iron-rich nuclei arranged in a lattice tens of billions of times stronger than steel. Yet magnetic fields, especially for magnetars, twist and strain this crust relentlessly. Over centuries or even decades, tension builds. The crust resists until it doesn't. When it gives way, the resulting starquake can release as much energy as 10 to the 15th lunar quakes combined. A crustal plate may shift by millimeters or centimeters, but the energy liberated floods the magnetosphere, accelerating particles and generating flares that span the electromagnetic spectrum. These outbursts can saturate X-ray detectors from thousands of light-years away. Some starquakes trigger brief, violent bursts of gamma rays. Others cause the neutron star's rotation to jump in a glitch, revealing the deep coupling between crust and core. These cracks aren't merely geological episodes, they are restructuring events for the entire magnetosphere. A shift in the crust forces magnetic field lines to snap, reconnect, twist, or fling out loops of plasma. A single quake can temporarily destabilize the entire surface, producing secondary bursts, afterglows, and chaotic particle flows. But starquakes are only one kind of violence. Another emerges from the star's relentless gravitational hunger. Many neutron stars have companion stars, sun-like or massive neighbours whose outer layers are slowly pulled into an accretion disk that funnels matter onto the neutron star's magnetic poles. When this hydrogen and helium-rich matter crashes onto the surface, it spreads, heats, and piles up into a thin, dense layer. As more matter accumulates, pressure rises. Temperature climbs. Nuclear interactions begin to spark beneath the surface. Then, abruptly, the entire layer ignites. This is a thermonuclear X-ray burst, a runaway reaction triggered when accreted material reaches the conditions necessary for explosive fusion. Hydrogen fuses into helium. Helium fuses into carbon and heavier elements. The surface releases energy equivalent to millions of hydrogen bombs detonating simultaneously, all in a flash lasting seconds. The rising fireball expands the thin atmospheric layer, pushing it outward. Observers see a surge in X-rays, then a cooling tail as the surface settles back down. The process repeats in cycles of hours or days, depending on the accretion rate. Some neutron stars even undergo superbursts, far more powerful events that ignite deeper carbon layers heated over years. These superbursts can last hours, flooding X-ray observatories with data and revealing the thermal structure of the deeper crust. Accretion doesn't only cause explosions, it also sculpts the neutron star's surface into complex, asymmetrical patterns. Where matter flows along magnetic field lines, it funnels toward the magnetic poles, creating accretion hotspots, glowing, biting circles of intense heat. As the neutron star rotates, these hotspots sweep across our view, creating X-ray pulsations. By studying these pulses, scientists can reconstruct the size, shape, and temperature distribution of the spots, and even infer gravitational bending of light near the star's surface missions. Like NASA use these rotating hotspots to map the neutron star's geometry and determine its mass and radius. The interplay between accretion, magnetic fields, and rotation creates a turbulent plasma environment. Near the magnetic poles, matter flows along curved field lines, colliding with the surface at relativistic speeds and producing shock waves, radiation pressure battles, incoming plasma in a complex feedback loop. The hotspots grow, shrink, split, or wander according to shifts in magnetospheric structure. Above these regions rise magnetic arches, vast loops of magnetic field lines reminiscent of the Sun's coronal loops, but scaled up in strength by factors of trillions. These arches confine plasma heated to millions of degrees, guiding charged particles along curved paths. When the arches reconnect or collapse, particles are flung outward, releasing bursts of high-energy radiation. Sometimes these arches interact with accretion flows, creating flickering X-ray brightness patterns. Sometimes they tangle with one another, storing enormous tension before snapping in magnetic reconnection events. Near the magnetic poles, the arches may channel matter into narrow jets or sculpt the magnetosphere into twisted configurations that cause repeating bursts. The dances of matter and magnetism do not end here. Neutron stars often sit near a boundary where classical physics dissolves and quantum electrodynamics dominates. One of the most dramatic examples is the formation of electron-positron pair plasma. In magnetic fields approaching 10 to the power of 10 to 10 to the power of 11 Tesla, the vacuum becomes unstable. The field energy is so high that photons can spontaneously convert into pairs of particles, an electron and its antimatter twin, the positron. This plasma appears in layers or clouds above the surface, interacting with the star's magnetic field in astonishing ways. It can scatter radiation, create pulsar beams, and sometimes contribute to magnetar bursts. The presence of this pair plasma is essential for understanding pulsar emission, particle acceleration, and magnetospheric currents. These plasmas behave unlike any earthly plasma. They are influenced by the quantization of particles in strong magnetic fields, the curvature of space-time, and the extreme density of field lines. Instead of moving freely, they slide along magnetic trajectories, emitting radiation that carries the signature of the magnetic environment. In the presence of a magnetar-level field, even the vacuum bends. This is vacuum birefringence, a phenomenon predicted by quantum electrodynamics and for decades thought too subtle to observe. In normal conditions, vacuum has no effect on light, but in magnetic fields millions or billions of times stronger than anything possible in a laboratory, the vacuum becomes polarized. Light traveling through it splits into two polarization modes that propagate differently, much like light passing through a crystal on Earth. In 2016, using the Very Large Telescope, astronomers observed polarized light from a neutron star called RxJ 1856.5-3754, finding evidence consistent with vacuum birefringence. This was the first observational hint that the vacuum itself behaves as a medium near neutron stars. These phenomena are not isolated curiosities. They interact with each other constantly. Starquakes twist magnetic field lines, altering pair plasma structures and triggering bursts. Accretion alters magnetic topology, creating or destroying hotspots. Vacuum birefringence shapes the polarization of emitted light, allowing astronomers to probe regions otherwise invisible. All of it happens on the surface of a star the size of a city. All of it plays out within a thin layer only a kilometre thick. All of it is governed by physics pushed far beyond the regimes humans can replicate. And yet, every burst, flare, pulse, and polarization shift gives us clues about the deeper layers below, about the superfluid interior, the exotic core, and the structure of spacetime itself. The surface of a neutron star is not merely the boundary between vacuum and matter, it is the threshold of an entirely different universe. One where forces converge at their limits, where quantum mechanics and general relativity intermingle, and where even empty space becomes active. Layers of complexity rise above that surface: magnetic cages, particle winds, shock fronts, reconnection zones, relativistic halos. Each phenomenon tells its own part of the neutron star's story, a story written not in gentle landscapes, but in eruptions, fractures, and quantum storms. There are deeper mysteries to explore still: the inner core, the interplay of quarks, and the gravitational echoes of warped spacetime. There is a quiet strangeness in contemplating a neutron star. Not the violent birth, not the magnetic storms, not even the swirling beams of radiation that sweep across the darkness, but the very idea of what a neutron star is, a place where matter reaches the end of its structural identity, a place where atoms, the building blocks of everything familiar, collapse into something simpler, denser, and more absolute, a place where physics reveals both its strength and its limitations. It is often said that a neutron star is matter at its limit. The phrase sounds poetic, but it is literal. Everything we know, from your body to mountains to planets to stars, is built from atoms. Atoms have structure, a tiny nucleus, a cloud of electrons, a balance of forces that allows them to resist compression. This structure gives matter its personality. It determines why iron is hard, why water flows, why diamonds sparkle, why air has weight. Destroy those structures, erase the spaces within atoms, and matter changes. It becomes unrecognizable. A neutron star is where nature removes the last vestiges of atomic architecture, where electrons and protons merge into neutrons, where neutrons themselves press against quantum rules that barely allow them to exist. It is not a place of many forms, many phases, many textures. It is matter pared down to its most stubborn and essential self. This makes a neutron star both incredibly simple and deeply complex. Simple, because it is largely one kind of particle. Complex, because those particles interact under pressures and densities that twist quantum physics into shapes we are still trying to understand. There is a quiet beauty in how nature chooses to store complexity in small volumes. Look at the universe on the largest scales, galaxies, filaments, voids, and you see matter spread thinly, almost delicately. Space is mostly emptiness. Stars sit like lanterns in a vast, dark hall. Entire galaxy clusters drift through an ocean of almost nothing, and yet, here and there, the universe compresses its matter into tiny spheres, white dwarfs, neutron stars, black holes, as though it wants to gather its secrets into compact archives. A neutron star is one such archive, the leftover memory of a massive star condensed into a sphere the size of a city. A place where nature takes the sprawling, chaotic life of a star and folds it into a single, ultra-dense page. Why would nature compress complexity into tiny spheres? Part of the answer is physics. Gravity demands it. But another part feels almost philosophical. The universe expresses extremes by making them small. The most intense gravitational fields exist in objects too small to see with the naked eye. The strongest magnetic fields bloom from surfaces only tens of kilometers wide. The highest densities reside not in galaxies or clusters, but in these compact remnants of stellar evolution. It is as if the cosmos chooses these dense objects as punctuation marks. Full stops at the end of a star's sentence, places where the narrative breaks and reforms. This compression brings us to one of the most haunting boundaries in nature, the boundary between existence and collapse. Neutron stars sit just above that threshold. Black holes sit just below it. The line between them is razor thin. Add a little more mass, just a fraction of a solar mass, and a neutron star cannot hold itself up anymore. Neutrons collapse into quark matter, or something even more fundamental, and the object becomes a black hole. Gravity succeeds in overwhelming all forces. The star has no surface, no crust, no atomic memory. Only an event horizon remains. Take away mass, just a little, and the neutron star sits safely in its quantum-supported state, held up by neutron degeneracy and nuclear interactions. This boundary is one of the most delicate in physics. It marks the limit of matter's ability to resist gravity. It is the point where structure yields to geometry, where particles yield to space-time, where force yields to inevitability. A neutron star is not stable because matter is strong. It is stable because quantum rules refuse to yield until the very last moment. This makes neutron stars invaluable, not only as astronomical objects, but as laboratories for physics, laboratories unreachable on Earth. We can recreate temperatures comparable to stellar cores in particle accelerators. We can produce magnetic fields millions of times Earth's. But we cannot produce gravity a billion times stronger than Earth's, or densities where nuclei melt and quarks swim freely. We cannot produce environments where the nuclear force, electromagnetism, gravity, and quantum mechanics all speak at maximum volume simultaneously. Only nature can do that, and it does so inside neutron stars. Every observation of a neutron star, every pulse of radiation, every X-ray burst, every gravitational wave chirp is a data point for physics at its limits neutron stars teach us about. The equation of state of dense matter, the behavior of superfluids under extreme pressures, the coupling between magnetism and gravity, the mechanisms of nuclear reactions at ultra-high densities, the nature of space-time near collapse. They also force us to confront questions about identity. What is matter when its structure is erased? What do particles become when they are crushed into near uniformity? Where does complexity go when it is no longer allowed? The philosophical implications expand further when we imagine something impossible but illuminating. What if a teaspoon of neutron star matter suddenly appeared on Earth? Begin with the fact that this teaspoon would weigh 1 to 3 billion tons. It wouldn't sit in your hand. It wouldn't rest on a table. It wouldn't even fall. It would collapse downward, pulling Earth toward it, not the other way around. The neutron star matter would immediately lose its support pressure. The quantum degeneracy that allows it to exist only under immense gravity. Outside that environment, the matter would decompress explosively. Neutrons would decay into protons and electrons. Radiation would flood outward. A violent, expanding fireball would erupt as the compressed matter reclaims atomic space. But it wouldn't stop there. The gravitational well of the teaspoon alone would be deep enough to tear up the surrounding crust. Earth's surface would deform around it. The matter would burrow toward Earth's center like a meteor made of pure gravity, vaporizing everything in its path. Even calling it falling is misleading. Earth would fall into it. As the matter decompresses, temperatures would spike to billions of degrees. The fireball would expand outward, igniting the atmosphere. Oceans would flash boil, the crust would buckle. The entire planet would be disrupted, perhaps destroyed. Neutron star matter cannot survive on Earth, and Earth cannot survive neutron star matter. This thought experiment reveals something profound. The stability of matter is contextual. Matter behaves one way under human-scale pressures, another inside stars, another inside compact remnants. Physics is not a monologue spoken in one tone. It is a multilingual phenomenon, speaking different dialects depending on the environment. Neutron stars speak the dialect of extremes. Thinking about these extreme environments also highlights a strange symmetry in nature. Neutron stars are terrifying in their density, gravity, and magnetism, yet they are also precise, predictable, rhythmic, even elegant. Pulsars rotate with perfect timing. Magnetic fields guide plasma with delicate structure. Superfluid interiors flow without resistance. Crusts crack in quantized, measurable ways. It is hard not to feel some admiration for a cosmos that produces objects so violent yet so ordered, so compact yet so expressive. They force us, unavoidably, into philosophical territory, into questions about the limits of matter, about the architecture of reality, about why the universe allows such extremes, and what those extremes teach us. Neutron stars are the punctuation marks in the story of stellar evolution, but they are also questions written in matter and gravity. They ask us to look deeper, to understand not only what matter is, but what it can become under pressure. They force us to think not only about stars, but about the underlying laws that govern everything. In contemplating them, we confront the thin boundary between existence and collapse, a boundary written in quarks, neutrons, and space-time itself. Somewhere in the darkness, far from the warmth of any sun, a neutron star spins silently. It does not shine with the soft glow of an ordinary star. It does not billow with plasma or swell with light. It simply turns, precise, compact, impossibly dense, the fossilized heart of something that once burned magnificently. It is strange to think of them as fossils, yet that is what they are, the remnants of stellar giants that lived full lives, forged elements, bathed planets in heat, and then collapsed under their own weight, their outer layers scattered into space in supernova flashes that seeded galaxies with the elements of life. What remained did not die. It condensed, it compressed, it transformed. A neutron star is a memory that learned to hold itself together. When you imagine what it has endured, the crushing collapse, the eruption of a supernova, the sudden freezing of its internal structure, it seems miraculous that anything remains at all, and yet what remains is not fragile. It is stronger than any material the universe can produce under gentler conditions. Its crust, its magnetism, its superfluid heart, all of it is order forged from chaos. Despite their violence, neutron stars possess a kind of elegance. Each pulse of a pulsar is a rhythmic whisper. Each gravitational wave from a merger is a note in space-time. Each starquake is a reminder that nothing, not even matter itself, is immune to tension. They are small things holding vast truths. The universe is full of contradictions like this. Black holes hide everything. Neutron stars reveal everything. One consumes the world around it. The other preserves what is left. Neutron stars are the archivists of stellar history. Inside them lies the record of a star's lifetime, its mass, its fusion history, the violence of its final collapse. The universe compresses those stories into a sphere only about 20 kilometers, 12 miles across. It is astonishing that something so tiny can hold the mass of suns, the pressure of galaxies, and the memory of beginnings older than Earth itself. When we look at a neutron star, through X-rays, through timing arrays, through gravitational wave signatures, we are looking at a relic, a perfectly preserved artifact of a star that once towered millions of kilometers wide. A monument to extremes. The more you think about it, the stranger it becomes. These objects spin like gyroscopes. They radiate beams, sharp enough to measure microseconds. They endure magnetic fields powerful enough to tear apart atoms. And yet all of it happens in silence, a silence deeper than any place we can imagine. There is beauty in that silence, a beauty not made of light or colour, but of form and function. A neutron star does not need to be loud to be extraordinary. It simply is. Its existence is enough to stretch our understanding of matter, gravity, quantum mechanics, and time. It is as if nature placed these small objects throughout the cosmos as reminders that complexity does not always require size, that the universe can be grand in ways that are compact, precise, and easy to overlook. Their pulses cross galaxies. Their magnetic storms can reach across light years. Their mergers shape the chemical makeup of worlds. A grain of gold in your hand may have begun as debris cast outward in the kilonova wind of two neutron stars, spiralling together long before our sun ignited. Every atom has a past. Some of that past is written in neutron stars. And when you step back from the science, from the equations, the pressures, the magnetic fields, you're left with something quieter. A simple realization. These small remnants carry more than physical information. They carry perspective. They show that endings can be beginnings, that collapse can leave behind clarity, that nature's most intense moments often create its most lasting structures. As the episode slows, imagine drifting away from the neutron star you've been visiting in your mind. The fierce gravity softens, the bent starlight straightens, the pulses fade into the background hum of space. Distance grows, the star shrinks once more into a point of faint X-ray glow. You return slowly to a world where gravity is gentle, where matter is spacious, where time flows evenly. The immense tension of the neutron star recedes like a distant memory. Let your breath loosen, let your shoulders soften. Let the universe feel quiet again. In the background, the familiar crackle of the fireplace returns. Steady, warm, human. The kind of sound that pulls you back from cosmic scales into the simplicity of your room, your evening, your moment of rest. Neutron stars will keep spinning out there, marking time with perfect regularity. You don't need to follow them. You can just let them be. Small anchors in a vast universe, holding their secrets until you're ready to visit again. Thank you for being here and for spending this time exploring one of nature's most astonishing creations. Let the fire crackle. Let the night deepen. Let your thoughts drift as lightly as you wish.